A part 2 video podcast for chapter 16 on lumped hydrological modeling. So in the first part, I covered just the general idea of modeling and the different kinds of models. Now we want to get right into hydrological modeling. In the long run, in this whole section for the rest of the course here, we want to get into fairly complicated models that are going to deal with ecology and a variety of applications of hydrology and ecohydrology. But for right now, we want to start with the most essential basics. How can we take rainfall and turn it into runoff? If you can do that, then you can pretty much do professional hydrology as entry-level hydrologist. And of course, a hydrological model is going to start with the hydrological cycle and compute the elements of the water balance with a special eye towards calculating runoff. There shouldn't be any surprise in the processes that you see on this slide. Just a reminder of what we're after. So what we do is we take that graphic and we turn it into a flowchart schematic. In this flowchart, we tried to list all of the individual stores and processes that are taking place. So we have water stored as precipitation or evapotranspiration, and then it's going to flux from one to the other. Some of these are more fluxes, some of them are more stores. But the key is that we need to characterize all of the processes that are taking place. And then we just have to make interesting and challenging decisions about how much detail to represent each process. You could also see that this schematic breaks the land into the surface system and subsurface system. Obviously, water flows across the land surface boundary seamlessly, but still, it's very convenient to break the processes up this way, and the vast majority of models that are used do that. Okay, so the first process is obviously precipitation, and we can represent precipitation with something called a hydrograph. Just as a hydrograph presents the change in discharge through time, a hydrograph represents the change in precipitation through time. In this case, showing it in terms of rainfall, but it doesn't necessarily have to be rainfall. This is just your typical histogram of the amount of rain discretized into minutes in this case. Now, obviously, you can't make a hydrological model if you don't start with the rainfall and turn it into runoff. But of course, the majority of uses of hydrological models is not to model some past event, but to conduct planning to figure out what would happen in different idealistic scenarios. So for example, you could say, well, I'm worried about the 100-year flood. Well, how much rain do I need to represent that flood? And how do I distribute that rain through time? So as a result, we need a synthetic distribution function that's going to represent the hydrograph through time. It's easy to specify an amount, but how do you specify that pattern? This is like the rainfall equivalent of the natural flow regime on an event basis. Well, for a lot of the things I'm going to show you in this video podcast, government scientists have done a lot of work all over the United States to try to figure out how the processes vary geographically. This is a relatively simple, crude schematic that shows what was figured out. That basically across the United States, there are 4 different types of rainfall distributions through time. And you can see the vast majority of the United States falls into a type 2 category, where we are in the Central Valley falls into a type 1, and the Sierras have a type 1A. So what does that mean? Well, this shows the cumulative distribution function. So remember, a histogram is what we call a probability density function. So it just shows the incremental change through time, whereas the CDF shows a cumulative amount of water through time. So in Excel, you should be able to work pretty interchangeably if you have a histograph to convert, sum up the numbers to get the cumulative numbers, or subtract one from the next to get the probability density function. And so this shows the fraction of rainfall through time, and you can see that a type 2 event has a relatively slow increase in rainfall, then a huge amount of rainfall in a very short time, and then a small amount of rainfall again. Whereas type 1 and 1A are more gradual storms. They still have a peak, but it's just not as extreme as what you see in the type 2 and type 3 events, right? Yeah. Okay. So that's the rainfall side of how we're going to handle this. And you will be doing this in assignments, so it's important to have a basic understanding before you actually get into the thick of it. So now you take your rainfall and you want to remove water as a result of the losses that take place on the land. We've talked about a lot of those different kinds of losses already. So how do we put that into a model? And that's what I'm going to show you. So we're going to consider different kinds of losses. And then once you've removed the losses, then you have to take the excess water that runs off and then route it through the channel network. So how do we handle losses? So if we take the precipitation through time, which I've shown here again, the x-axis is time, y-axis is intensity of precipitation, then we can look at the losses as three different components. And now when I talk about these three components, I'm not talking about a specific process. I'm talking about, relative to this histogram, what these are. So in the initial instance, when rain begins, water is going to be stored. And it's going to store until eventually you have enough runoff that you have enough rainfall to overwhelm that storage capacity and have saturation excess. Okay? And so that's going to yield what is called the initial abstraction. And it's shown here in orange. Like these two, the first 12 hours or whatever in this case of rainfall are all consumed by the watershed. Like nothing runs off. After that, then I've got two different components to losses. I have a constant value that might represent like tree interception, transpiration might be constant, and possibly depression storage, but yeah, probably not. And then I've got the pink component here where the amount of storage changes through time, and that could be soil storage, and it could also be depression storage because that can grow as different areas of depression are filled up. So what we're going to do is we're going to look at different ways of doing it and then go through the most common way that's used in a lot of the consulting world. The first thing is you could assume each of these terms are constants, but that's a relatively poor choice. Another thing you could do is you could get a very complex equation for each term, maybe go out in the field and calibrate it for your site, and then apply those. And certainly there are models that do that. But a more common approach is to do a lumped approach. So in the same way that we can treat the whole watershed as one entity and talk about that being a lumped watershed model, we can also lump the processes. So if we take all the processes that remove water and lump them all together into one representative process, we just call it loss, then we can do that. So what I want to show you next are some simple equations that are very conceptual, that can be employed to create a hydrological model that does this removal of losses. Of course, we're going to begin with the water balance, right? I mean, you got to have a water balance if you're doing a hydrological model. It's a basic law of mass conservation. So here I've written the water balance. Instead of like inflows equal outflows plus storage, I've just solving it in terms of the runoff or stream discharge Q, and it's going to equal the gross precipitation minus the initial abstraction minus water that is retained in the soil after the initial abstraction period. So initial abstraction, that lots of things lumped together. And even the infiltration retained in the soil, it still could be a lot of different specific, stores that are holding that water. So here's a water balance equation. Now, we can't just solve this equation without some mechanistic aid. Ideally, you'd want to have a momentum equation. You take mass and momentum together and you can solve that system. However, that's a relatively complicated model to solve. So usually you have to either simplify the momentum equation down, or you have to substitute some kind of concept or what we could call a rule that's going to govern flow or storage in some way. And so what happens is that there's a method called the Soil Conservation Service rainfall runoff depth relation that provides the key ingredient we need to complete this model. What we do is we say that the amount of water that runs off is proportionally similar to the amount of water that's retained as a function of total storage. Okay, so on the left side, we look at the fraction, the amount of water that's actually stored compared to the total storage, and the amount of water that runs off compared to the actual, with the actual amount that runs off compared to the total water available to run off. And so the idea here is that these would remain proportional. So this is a linear transport law, essentially, that tells us how runoff would function. Without going any further, let's just try to understand this, because there's just no way that we just pull this out of a hat. It can't possibly make any sense. But let's just play with some numbers. Okay, so let's look at two different watersheds with different storage capacity. So in this case, S is total storage of water that we can have. So let's have a rainfall of 4 inches in this storm, and let's have an initial abstraction of 1/2 inch. So if we go to the mass balance equation, 4 minus 0.5 equals 3.5. So the runoff is going to equal 3.5 minus the infiltration that's retained. And then we can similarly put in 3.5 down here. Okay, now let's have one watershed with a storage of 3 inches. That's the maximum capacity of water that the soil can hold. And have another watershed with a storage capacity of 2 inches. If we put the numbers in, we have two equations. So the first equation on the right simplifies to this here. On the left. And then we have the mass balance equation. So if we substitute in the I retention equals 3 over 3.5 Q into the equation below, then we can eliminate it and solve for Q. Once you solve for Q, then you can come back to either of these equations and solve for I. And what we find is the numbers that are given here, and then if we do Q over P, we can find out that the fraction of total water that, the net, the fraction of the total water that rains down out of the sky that actually runs off is 0.47 or 47%. If we come to watershed 2, we go through the same process. We just put in a 2 instead of a 3, and we find out that we get more runoff. So, the watershed has less soil storage capacity, and as a result of that, you have less water retained in soil, more runoff, and indeed a higher fraction of runoff. So I hope what you're beginning to see through this example is that the proportionality creates a very common sense outcome. That is that if a watershed has less total storage of water capacity, you're going to get more runoff. And that's what this linear model does for you. The other thing we could do is hold the storage constant and change the precipitation. So let S equal to, the initial abstraction remains 0.5, and then let's compare storms of 3 or 4 inches. And you just put those numbers into the equations from before and solve, and you'll find that a small storm has a lower fraction of runoff, and a large storm has a higher fraction of runoff. So in essence, this very simple pair of equations, a mass flux equation and a simple rule, for linear runoff in proportion to linear storage, is getting at the key process for how watersheds actually might work. So if we take those two equations and we formally put them together, we can come up with this analytical solution that discharge equals a ratio of the net precipitation, PG minus IA squared, divided by the net precipitation plus storage. And I'm not going to work through those steps. They're pretty easy algebraically. So the problem here is we have one equation with 3 unknowns. We don't know PG, we don't know IA, and we don't know S. So this equation is not lumped enough. We have to do more lumping and more simplification. So the next thing is you send out all your scientists around the United States and you make measurements and you find out, hey, initial abstraction is actually related to storage. And in fact, initial abstraction equals 0.2 of the total storage capacity of the soils in the watershed. So knowing that, and I can only imagine what the scatter plot would look like for an analysis like that, but nevertheless, you can take that equation, substitute it in, and now we've reduced the equation down to 2 unknowns. So to estimate runoff, if we know what rainfall amount we're interested in, then all we have to do is estimate something about S. How do you determine what that capacity is? And then you come to the realization that that storage isn't just a function of soil, but it's also a function of land cover and land use. You may have highly permeable, highly porous soils, but if you have a parking lot over it, as we've already covered in the class, you're not going to get any storage. So we have to have a way to account for that. So now we're going to go again for another time to shift gears and try to characterize storage in terms of some land surface, land cover, soil characterization. To do that, the Soil Conservation Service created the idea of a curve number, which is represented by these letters CN. So a curve number is something that you can look up in a table, and I'm going to give you a handout that will show that. You find out that the soil storage equals 1,000 over CN minus 10. So this is another empirical equation to get at a more tractable empirical parameter that we can use to characterize the storage capacity of watersheds. So what is this curve number? There are lots of standard tables. If you go into Google or you look up a hydrology textbook, you'll find these tables. It'll tell you that, if you're a residential neighborhood, you have a curve number of 70. If you have this soil type, you have a curve number of 40, and so on. And so I'm going to provide the class with a handout on estimating runoff curve numbers, and you'll see that it's a function of land cover, land use, and soil characteristics. So overall, you've got the whole arc of this thing. You've got two equations, one of which is a water balance equation, one of which is like a transport type rule, and you're putting that together with a whole lot of empiricism to make it tractable. And in the end, you have to just say something about the land cover type, again, lumped for the whole watershed, and feed that in. So it's not like, part of the watershed is urban and part is rural. Like the whole patchwork thing that has been the basis of this whole class, just throw that all out the window for right now. You have to somehow aggregate all of that up and get one number, one curve number to represent the watershed. So the nice thing about this is it does include some physical ideas. It is deterministic. It only has one parameter in the curve number, which is easily obtained in GIS, and you'll be going through an assignment not using GIS, but to do that manually. The weaknesses is that it's got a whole lot of empirical crutches that are black boxes that most people have no idea what's in there, and when you look in there, there's a lot of limitations that come into play. This is a graph that just conceptually illustrates the outcome of the curve number approach. It's a nonlinear outcome in the end because, of course, when you look here, you have this square, and so it's going to have to be a nonlinear result. But what you what you can see is that for any given rainfall, let's say you have 6 inches of rainfall, and let's say you have a curve number of 60. So I go along that curve number, come down to a rainfall of 6, and I find that my cumulative direct runoff is going to be 2 inches. So if I increase the rainfall from 6 to 7 and I stay along that same curve number because I'm not changing the land, then you arrive at here like 2.7 or whatever. On the other hand, if I have 6 inches of rain, but then I urbanize and I go from that 2 inches of runoff and I go to a curve number of 100, then I get 6 inches of runoff, which is 3 times. And actually that sounds pretty reasonable from some of the numbers that we've seen on the effects of urbanization. Okay, so what I want to do is I'm going to give you an opportunity for extra credit in the class, which is take the equations that are shown on the slide and solve them to produce a graph with curve number on the x-axis and discharge on the y-axis. For the gross precipitation, why don't you pick a value of like 7 inches of rainfall, let's say, and for a range of curve numbers, find out what is the runoff. Now, why am I asking you to do this as a bonus? The reason is that one of the themes of the class is to look at the effects of human activities on hydrological cycle and eco-hydrology. Well, the curve number is this model's way of representing those impacts. So you can imagine a curve number for a natural, well-forested landscape with patches of wetlands and everything else might have a low curve number of like 30, whereas like a agricultural grassland with a lot of cows that have stamped down on the ground might have a curve number of 70 to 80, and then an urban area with a lot of pavement might have 90 to 100. So one way to assess the effects of human impacts on runoff would be to see, as curve number increases, what's the change in discharge through time. So that's one way to look at it. And you could pretty much recast all of the questions we've asked about urban into a format where you could answer it with, I'm sorry, not just urban, but deforestation, like all the human impacts. You could assess that in terms of this model. Okay, so everything I've been talking about there, we've covered how do you get the rainfall, and then how do you go from rainfall to runoff. But now you've got the runoff at the mouth of that watershed, and now potentially you may need to move the water from the mouth of that watershed down through the river corridor to some other outlet, right? You could just have one overall lumped model for a whole watershed and just boom, you're done. Or you could break the watershed up into smaller subbasins and then route the water from one basin down to the mouth of a larger basin. And that's a process called routing. And it would be beyond the scope of this class to go into the methods of how a unit hydrograph, what is a unit hydrograph and how does it work. But a unit hydrograph, just summarized here, it's the response of a basin to a unit of rainfall excess that's uniformly distributed over the area over a given time. I actually gave this definition in the urban lecture, but it's not a high priority. And we're not going to go through the process of how this is all computed. But the important thing is it's treating the watershed as a linear additive system. So you can imagine there's a couple ingredients that we need to figure out for this to work. What's the peak of the runoff going to be for whatever we want to know? And then when does that come? And so to get to this time thing, you need some way to compute a variable known as the time lag. Time lag is the time it takes for water from the most distant point in a watershed to reach the outlet. So that means if I were to start, like, I don't know, maybe this is the most distant spot, water is going to move relatively slowly to get to the stream head, and then from there it might move relatively quickly to get to the mouth. Whereas somewhere over on the side, it might take actually even longer because it's got to go overland quite a long ways, and then it hits the stream. So it's not actually it's not the physically most distant point, but it's the hydrologically most distant point. And this is just a graph that shows like the time, the amount of a watershed that it takes each interval of time to receive the water from. I didn't say that very well. Okay, let's try again. So for each time, like let's say it takes 1 hour, like how much of the watershed can contribute its water in 1 hour? That's what this would be. Then you say, okay, well, now more of the watershed will have contributed by 2 hours and 3 hours and so on. So this is a cumulative distribution function that gives us the percent area contributing water for each amount of time that you're interested in knowing. I think that's a better explanation. Okay, so here's a hydrograph. You're all familiar with hydrograph. On the x-axis is time, on the y-axis is flow. The blue curve shows a real hydrograph. Now for a hydrological model, does it really matter the pure exact nonlinear shape of the hydrograph? If it does, this is the wrong model for you. But in most cases, it doesn't really matter. And so with the kind of modeling I'm showing you, we represent the hydrograph as a triangle. Okay, and so with this triangle, the variables that matter are the time lag, which is shown here. The time lag is from the beginning of excess precipitation that's actually running off after initial abstractions are done until the peak. And then, let's see, that's how the time lag is being represented here. And then we have the actual peak. So what is the peak? So here I talked about the time lag. It's the time it takes for water from the most distant point to reach the outlet. Presumably when that's happening, it's going to be associated with the peak, but maybe it's not always that way. So the way, okay, now I got it. Time to peak, there we go. Okay, so time to peak is the time from That's where we're okay. Right, the time to peak is the time that's going from the onset of rainfall excess until the peak. Right, so that's time to peak, and it's a function of the time lag as well. Okay, so there are some empirical equations that are used here to get at this, again, based on studies that have been done. So you start by calculating to time to peak as the duration of rainfall excess precipitation divided by 2 plus the time lag. And then you take that time to peak, you put it into this function here, and you get the peak discharge equals 483.4 times A over T peak. So there's a lot more detail that you could go into to try to understand why it is the way this is. To do that, I'll be showing you some manuals that will be going into that more, and that's just beyond the scope of the class, because what I really want you to do with this model is to just get the conceptual idea of it, that we can represent the hydrograph in terms of a peak discharge and a time to peak, and then we can take that and use that to run the model. And the model that we're going to be playing with is a very standard model used in consulting and professional hydrologic project practice in the United States, which is the United States Army Corps of Engineers Hydrological Modeling System. So there's a branch of the Army that's called the Hydraulic Engineering Center, HEC. It's actually located here in Davis, California. And the HEC has a model that today is called HMS. Historically, it was called HEC 1. And HEC 1 is the most simple, efficient way to go. HEC HMS has a nice user interface and a little bit more graphical button pushing, but the nuts and bolts are still essentially what's in HEC 1. It's just added a lot more bells and whistles and ways of looking at it. So what you do with a lumped model like HEC HMS is you take your watershed, as shown here in this schematic, and then we're going to divide that into subbasins. Now, the hard part that you really need to understand is that this subbasin delineation, that these basins can be, each basin has a unique area, but water from one subbasin can flow into another. So, for example, let's look at this subbasin 10. Okay, here the dashed line represents the watershed boundary for that. So water cannot flow across the dashed line. All water within area 10 is going to come to this one outlet point at the channel. From there, the water is going to have to be routed to the next point, which is the mouth of 20. So 20 is this strip that's bounded by these two dashed lines, and that area, then you compute the amount of water contributed there. And so you can see each one of these has its own area, and then how flow moves from one to another is represented in the schematic on the right. This is relatively similar to the kind of schematic I was asking you to draw for the Salinas River assignment back when we were looking at rangelands. I gave you that assignment to start preparing you to think about what you're looking at right now. That was kind of foreshadowing this. So what you see here is like watershed 10 flows into 20. 20 also receives water from 40 and 30, but in addition to that, it generates its own water. So the squares here represent a rainfall runoff process, and then 20 represents a combination point where you're linearly adding all the water at each time step as it arrives at that point. Then water from 20 is routed down to 50. 50 has its own water that it contributes. It routes all of that to 60, and then 60 adds its water, and then down to the reservoir, which is shown with the hatched line. So that's the general concept of how this model works. Again, until you're hands-on with this, I know it's going to be hard to think about it. So we will, of course, have assignments that deal with this. This is what an output would look like from this type of model. You have discharge through time. It's a transient flow. It produces a hydrograph. So it's a deterministic model as opposed to stochastic. It's lumped in the sense that, even though we break the watershed into a few subbasins, we're still treating large areas with one set of land cover numbers. So it's, it's spatially lumped and also process lumped. So there's two different ways of defining that concept of a lumped model. These models are generally event-based because they don't track soil moisture through time. So you're going to use this to get one hydrograph. Dynamic, and that means it changes through time. There's a single scale, which means that the processes of initial abstraction and soil storage and land cover effects, they're all regardless of how big or small you make your watershed, you use the exact same equation. It's not scale dependent. It's only looking at the most significant processes. We've greatly simplified the physics of the problem. And this is used as a resource management tool, not as a scientific exploration tool. So what are the steps in a HEC HMS model? And of course, you'll be doing these steps very soon. Compute the rainfall runoff for each subbasin, route flow from each subbasin to the next stream junction, combine flows from subbasins that are at that junction, and the route flow from junction to junction down to the mouth. So I've already walked you through that once, but I'm just hitting it again. In a nuts and bolts way, what do you need to do to actually run HEC HMS or HEC 1? And I'm kind of using those somewhat interchangeably. I mean, the more you go towards the graphical user interface, then the cookbook sort of changes. From my perspective, it's really helpful to start with the most basic fundamental model in HEC 1 and understand how that works, and then pick up the graphical elements on your own or in your job. Of course, you're going to need to get all your data sources, whatever information is going to drive the curve number characterization, and your precipitation information. What are the size events that you're interested in? The 100-year event, the 10-year event, and so forth. Then we're going to have a text file. You're going to love this. You take all this information, you put it into a simple text file. If you're on a PC, that's going to be like Notepad. If you're on a Mac, you can use TextEdit, but you can't run this software on a Mac, so you'll have to convert it over to a PC. You run the model. To run the model, so to speak, there's nothing magic about it. You just double-click on an exe file on a PC. It reads the information from the input. It runs and produces the output. The output is another text file. You can copy and paste information out of that into Excel and parse the data out using a function in Excel called text to columns. So don't manually type the numbers in. Of course, with the graphical interface in HEC HMS, you can produce a variety of outputs that can be directly used to generate graphs internally in that software or to bring it into other software. Analyze model results. Okay, so imagine, if you've never done any computer programming before, a computer program is nothing more than a line-by-line set of instructions telling a program what to do. Welcome to computer modeling. The way HEC 1 works is that each line in this text file begins with a 2-letter code that tells the model what to do. The first code, like ID, it doesn't tell it anything. It's just saying, hey, here's the identification for that model run. IT, set the time step, and a few others. But the next part is we have to start computing the hydrographs. And each one of these codes, and I'm not going to read through them all, but we'll be working on this in class, and you can look through both the HEC 1 manual that I've provided for you, as well as these slides to see the different kinds of things that you can do. I'm going to provide you with a template file that has the basic nuts and bolts and placeholders, and then you just have to put the correct numbers for the sample data in to the files and run it. So there are codes where for each individual line you're going to be computing the rainfall to runoff process. Then there's going to be the hydrograph routing, moving water down the system, and then combining the hydrographs together. Let me just illustrate this with a practical example of what you might do in a consulting project. Here's an example that I found for South Tobacco Creek, which is located in south central Manitoba, Canada. It's an agricultural watershed, low relief. There's a lot of dams. So if you look at this area, the outlet is where the diamond is, and then the black line is the watershed. Every black dot that you see is a dam in the system. And then I believe that the shaded kind of bluish area is the total area of land that is contributing to a dam, and then where it's white, those are areas that are unregulated. So given these 26 small dams, you could ask a management question like, how effective are these dams at abating the instantaneous peaks associated with different return interval events? right? Because remember, the peaks are going to hinge on the size of the event, and dams are just a form of storage, so you know very well by now that the hydrological effectiveness of storage is dependent on the frequency of the event. We could also ask the question, what if we were to switch from 26 small dams to one big dam? Maybe if we had one big dam, we wouldn't be creating watershed effects all over the place. We could consolidate the damage, so to speak, into one area. Alternately, maybe 26 dams give us more flexibility to turn things on and off, whereas one dam can't be flexible at all. And then finally, we're going to look at the effects for summer rainfall and spring snowmelt. And I think what this example is going to show you, without a particular validation, but it's going to show you in more of an exploratory mode how a model is very useful at giving you an idea of actual numbers for what the benefits or lack of benefits are. So we're going to model the pre-dam flood peaks with HEC-HMS using historical watershed data. Then we're going to model the post-dam peaks and see what the differences are. The first step is we have the subbasin area. So here's the number of subbasins and their contributing areas. Then we look for different runoff events, the 1 in 2 year event to 1 in 500 year event. What is the instantaneous peak flow that results from the model in a rainfall runoff scenario, and then what's the total volume of runoff that's there as well. And then we can do the same thing with the snowmelt case. Okay, so the next thing we can do is we can put in our 26 dams. So we have the natural runoff that was there, and so that's the same. You see this first column here is the exact same as the first column we had before. We can then put in the results that come of including the dams, and the third column shows the reduction in peak flow. So you can see anywhere from 13% to 25% benefit in terms of percent reduced flows. Notice that the greatest benefit isn't necessarily associated with the smallest storms, which is what I would have expected theoretically. But again, because of the complexity of an individual site, you can't just take a general concept and dogmatically apply it. You have to actually do the analysis and find it out. For snowmelt, we see less of effect and a little bit more like what I would expect, which is that a range of 9 to 19% reduction, with the largest events having the least benefit. And the main explanation there is just that snowmelt is not so much of an individual peak, but it's something that's happening through time. And so as a result, the model may not be as representative, and it's not, that a lot of things that are happening are not just related to the peak. Is one dam better than 26 small dams? Well, when we do the head-to-head comparison, the percent reduction of small dams versus the percent reduction for one large dam, where I've highlighted these like red bars, that's where the small dams have performed the best. And then the yellow bar is the range of return interval events for which the large dam performed best. So the large dam, performed about 30% better to 40% better if you compare the numbers compared to the small dams. But there were a few cases where it was the other way. So with a 5-year event, the small dams performed better. So overall, dams are effective at reducing the flood peak. Obviously, that's why we create them. They're less effective during spring snowmelt than during rainfall. I've already talked a little bit about that. Small dams, not as effective as large dam for most events. But on the other hand, there are other benefits to having lots of small dams instead of one big large dam. There's just a whole host, of course, when you get outside the modeling, a whole host of positives and negatives and all of this. And that's really beyond the scope of this. What I've tried to do is just cover a range of ideas about lumped hydrological models and introduce you to the idea of how you're going to actually run a model and what an analysis in consulting would look like using that model. So now we're going to start to work on the assignment to use HEC1 and see how it goes.